Afternoon. I'm Jim Nasby with Blue Trouble Solutions, and I'm going to be talking about data science and big data features in Postgres. Is anybody here a data scientist or doing predictive analytics, any data science type stuff? The concept of data science actually has existed for probably 20, 30 years. Certainly predictive analytics have been around that long. Some of the machine learning ideas have been around that long. It's only fairly recently that data science has become this kind of all-encompassing buzzword bingo term to be applied to that. Similarly, big data, which I recently heard, apparently that term was actually coined by Greenplum, which is a Postgres-related company, has also only been here for about 5 years. And what these two things share in common is that when you talk to a lot of people about big data or data science, the notion of using a relational database it doesn't make sense. They think that you wouldn't, there's no reason that you would want to use a relational database to do these kind of things. And I think that is unfortunate because there's many cases where a relational database gives you capabilities that you can't get otherwise or makes it easier to do your job. So today I want to try and go through some of these features that we have in Postgres that make it easier to do data science and predictive analytics. And roughly those features boil down to developer features, administrator features, performance, and then there's the community itself. So on the developer front, if I can get my clicker to work here, on the developer front, the main features that we have are JSON, this ability to connect everywhere, multiple languages, and extensible types. JSON, we've had that for a while now in Postgres since version 9.2. There are two different JSON types. There is an unparsed JSON, which is just the plain JSON type. That is essentially the same thing as a text field. The only real difference is that when you provide data to a JSON field, it does validate that it is legitimate JSON. But past that, the storage is exactly whatever you passed in, including all the formatting. Binary JSON, or JSON-B, what I think some NoSQL databases call BSON, that takes the JSON and it parses it down into an internal representation that's stored in a more natural, easier to use format for the database itself. As part of that, you do end up losing the formatting that is provided. The other thing you have to be careful of with JSON-B is that if you have two keys in a JSON object that have the same name, it is non-deterministic which one of those keys will actually make it into the document, but only one of them will, not both of them. And unfortunately, it does not actually throw an error if you do that, so you do need to be careful about that. There are two different ways for doing indexing. There's a bunch of operators, and importantly, there's strong data consistency with the other types within Postgres. So that type consistency becomes very beneficial because it allows you to do things like constructing JSON documents easily. So the row to JSON function is taking the t.star is saying, give me all the columns in this test table, and the true means to pretty print it. So we get this, fairly well formatted JSON object where the field names are the key names and the values of the data are obviously the values in the JSON document. There's corollary functions where You could take this same JSON object, feed it back to, I don't remember the name of the function offhand, but there's a function that does the reverse that will take that and say, okay, here's a Postgres composite type that contains the data that was in this JSON document. When it comes to data science, this is important because JSON has become kind of the new XML. It's very common to see data that is parsed and handed about in a JSON format. A tremendous number of web APIs use JSON. So having that capability within Postgres means that you are not dependent on an external application needing to do the parsing. This also means that you can store the unstructured data directly in Postgres natively. And in fact, now I believe that MongoDB has made improvements to their performance, but for a couple years ago, a couple different companies did tests comparing Postgres JSON performance to MongoDB, and Postgres was handily faster. Postgres also has an ability to connect to anything. There are foreign data wrappers, so those were added in 9.1. They allow you to take any kind of a data source that can be represented as a table and create what you can think of as a virtual table within Postgres, where when you query that table, it's going through the foreign data wrapper and talking to whatever the underlying data source for that virtual table is. There's approximately 100 foreign data wrappers. There is a wiki page that lists all of them. Amusingly, one of the foreign data wrappers is actually a foreign data wrapper for the wiki page itself. So you can get the list of foreign data wrappers in a virtual table within Postgres. There's 15 NoSQL foreign FDWs supporting 10 different databases. There's 7 kind of big data data wrappers for Elasticsearch, Hadoop, HDFS, Hive, and Impala. I said earlier, Postgres can connect to anything, and that wasn't actually really a lie, because Postgres also has the ability to do multiple stored procedure languages without any modification to the code. The only requirement is that you do have to write a language handler in C, but it's really not that difficult, and there's several examples you can look at. Perl, Python, and Tcl come built in. Java and R are out there. Both are very popular. There's Lua, V8, Parrot. There's several others. If the language that you'd like to use is not on the list or doesn't currently exist, you can add it. So when you combine the foreign data wrappers and the multiple languages, you really do have the ability to get Postgres to talk to any data source on the planet. Because if there's not a foreign data wrapper for it, you can always do it with a procedure language such as Python or the untrusted variant of Perl that allows direct connection. So you can have the database connect directly out. Postgres also has extensible type support. So you can create a brand new data type with full index support, full optimizer support, just like any of the internal data types. And again, you can do this without making any kind of modifications to Postgres. This can be extremely useful for a lot of big data type scenarios. So for example, if you're dealing with genomics and you're representing DNA information, AGCT, one way you could do that is to have a string of letters. But at 8 bits per codon, that's an extremely inefficient way to store that information. You can instead create an actual data type that stores that information much more efficiently. I've created Anyone use NumPy pandas? So I've created a data type that will take a NumPy ND array. This is something that is used very commonly in data science, and you can store an ND array directly inside Postgres. And that's somewhere on the order of, I think it's about 50 or 60 lines of C code. It's really not that difficult to create that type. And there are also transforms that are now available. Those I think came about in 9.4, that the transforms allow you to control how a non-built-in data type is handled by a stored procedure language. So prior to transforms, if you created a new data type, you couldn't really make too good of a use of it inside a stored procedure in Postgres because it would just be handed into the stored procedure as a text representation. So then you would have to know how to parse that text representation. You'd have to do it by hand. Not very performant, not very much fun. Now with transforms, you can create a transform function that understands how to go from the internal data type to whatever your stored procedure language requires. So for example, using the ND array data type, this is a, repr is a common Python function. It will give you a text stable representation of a, any type of Python data. So all that this function does is it accepts an ND array, this data type that I've created. I say, use the transform for the ND array type, and then all it's doing is returning a single Python function call. So using that with data that I've populated in a table, this is the text representation of what that ND array looks like. And for those of you who are familiar with ND array, this is actually a data frame. So this is essentially a table that is stored in a single field inside of a Postgres table. So when you're dealing with these kind of operations, you have a lot of flexibility now with what you want to do for storage versus computation. There's several administration features that Postgres has that lend themselves to big data in particular. There are two different backup options. This is useful because sometimes what you want to do, if you just want information from a single table or a few tables, pgdump is a much simpler way to do that than using the full-on binary backups. Point-in-time recovery is the binary represented backup that uses the underlying Postgres recovery capability that Postgres would make use of during a database crash to recover. So using that capability, you can take a binary level backup of the database using file system level tools. It makes it very fast and efficient. pgdump, on the other hand, is a complete SQL representation of what's in your database. The nice thing about pgdump is it's incredibly simple. You run a single command, you get your dump, you're done. There's no ifs, ands, or buts. Unfortunately, with point-in-time recovery, because of all the things that are in play working at the file system level, there's many different ways that you can potentially set up a binary backup system where you don't realize that your backup doesn't actually work. So as was said during lunch, if you don't test your backups, you don't have backups. But the nice thing about pgdump is that you don't really have nearly as much of a concern. If the pgdump complete successfully, you're much better odds of having a completed, usable, safe backup. And PG dump is not going to suffer from race conditions. Unfortunately, with the point-in-time recovery, there's a number of places in here where you can end up with race conditions where sometimes your backup works, sometimes it doesn't. So there's also multiple options for replication. Streaming replication, based on the binary level, it's highly efficient, and this can be truly synchronous. So one of the challenges that you can run into with NoSQL solutions is a lot of times they trade off scalability and availability for consistency. So if one of the nodes goes down, if you actually lose power to a data center, which is something I've seen happen, you can end up with your data in an unknown, inconsistent state. Whereas with Postgres, you can set up a replica that can potentially be off-site and make certain that anytime you commit a transaction, it is committed to that off-site replica. So true synchronous replication. And I believe it was added in 9.6. You can now do that. You can specify that not only is it on the replica, but it's actually visible. Whereas previously, it would just ensure that the data had been written to disk on the replica, but replay might actually be behind. That capability is controllable at an individual transaction level. So you can say in a specific transaction, this is data that's not all that important. So asynchronous is completely fine. When it gets to the replica, it gets to the replica. I don't care. And somebody in another session can say, this data is really important. This is somebody just bought something from us, so we need to make sure and record that. That can be done. You can specifically state for that transaction, I want this to be synchronously replicated over to my backup so that I know that it's written down in two places. PG logical is a logical replication method that allows you more flexibility in your replication. It allows you to do things that the binary replication does not allow for. One of the big things is that binary replication right now, one of its shortcomings is you cannot create temporary tables. Well, for doing things like predictive analytics, that can be an enormous problem. PG logical, because it's not binary level replication, it's only reading from the transaction log on the master and then streaming SQL statements to the replicas, you can create temporary tables. You can create real tables. So you can have analytics replicas that are specifically geared towards doing predictive analytics. You can create models. You can store the results of those models on the replica. And if you then need, you can move it back to the master, but you can do that work without impacting what's happening on your master database. This is something that really isn't, I don't think there's really any corollary to this when you come to NoSQL solutions. Typically, with NoSQL, it's just throw more nodes on the pile, throw more nodes on the pile. And if you end up in a situation where the sharding is not working in your advantage, or you're performing queries that for whatever reason are not balancing themselves across the cluster, you're kind of stuck with the performance that you're getting. So having that replication opens another option for you. There's also bidirectional replication. So this is multi-master replication. You can go both directions. You want to try and avoid writing to the same set of data on both sides of the connection, because if you do that, you can end up with conflicts, but those conflicts will be detected and there's ways to handle their resolution. This supports wide area replication. There are people that are using this on many node Postgres installations that truly span the globe. So it's very forgiving of latency. One thing to be aware of, though, is that this does employ an eventual consistency model. So it's similar to a lot of NoSQL solutions in that regard. There's several other logical replication alternatives that are out there. Sloaney and LoanDist are two of the most popular. Unfortunately, I don't think LoanDist is really being actively developed anymore. Sloaney, on the other hand, still is. Bucardo is another option. There is, I believe there's at least one other that's fairly well known. Bucardo is done at a driver level, and if I'm not mistaken, it mandates JDBC. So if you are using Java, it's certainly another option for you. There's a number of performance features that Postgres has that make it rather amenable to solving big data and machine learning challenges. I think one of the biggest features is not actually really a feature so much. It's more of a community methodology or a mindset, if you will, and that is that the Postgres community is constantly looking at ways to improve performance within the database itself. Every release of Postgres, pretty much, and it depends highly upon your workload and somewhat on your hardware, but in my experience, most major releases of Postgres will give you roughly a 10 to 30% performance improvement without having to do anything. You just put the new version in, get upgraded, and boom, stuff is just faster. That I think is tremendously important when it comes to dealing with big data, because the hardware is scaling, but the database is scaling along with it. So workloads that just a few years ago, there would be no possible way to run a certain workload on a single server. Well, now you can run it on a single server just because of the performance improvements, the concurrency improvements that have come in through Postgres. Of course, one of the big features in 9.6 is now parallel query execution. Currently, it's only supported for sequential scan, join, and aggregation, but more query execution paths are going to be parallelized as work continues with version 10. There is also cluster support for Postgres. And this, I think, is something that is really kind of a hidden feature in the NoSQL land of things, is that you can actually do a lot of the things that NoSQL allows you to do with straight community Postgres. So Citus Data has now open sourced their distributed database extension. This is implemented strictly as an extension to Postgres. They are not making any kind of modifications to core Postgres itself. So you don't have to worry about, have they introduced some bugs in the storage engine or anything like that. This is an extension that plugs in, sits on top of or alongside of Postgres, and gives you the ability to shard data across large numbers of servers using essentially hash partitioning, which is what most of the NoSQL implementations do. You can also have more than one shard for each piece of data, so you can get redundancy. Again, one of the features that the NoSQL engines tout. PostgreSQL is, that does make modifications to Postgres, but it gives you full acidity in a clustered environment by using a global transaction manager. So if you need really strong transaction guarantees and really strong consistency guarantees in the data that you're dealing with, that's another option that you have. Finally, Greenplum, which has been around for, I'd say, 5 years. Does anyone know when Greenplum was founded? This was really the first foray into both parallelism and shared nothing clustering for Postgres. It is a fork of Postgres 8.3, but they have pulled many of the features that have been added over the years, so that there's features even from, I believe, 9.5. I don't know if they've pulled anything from 9.6 in, but there are 9.5 level features in Greenplum, and again, this is a technology that started commercially and is now open source. Greenplum open source, that's I think it was last summer. Column stores are very powerful for dealing with certain kinds of data. So the notion here is that if you're accessing data in a table, but you don't need all the columns, you only need certain columns, or you're doing certain operations on the columns, a column store can be far more efficient because the data that you'd see in a column is actually stored sequentially together on disk or in memory. Whereas with a traditional table storage format, you're storing row after row after row. Even if you only want 3 columns out of 20, you have to read an entire row in to get at those 3 columns. So for terabyte-sized tables, the performance difference between being able to read just the data for 3 columns versus having to read the entire row, that can make an enormous difference. So column store FDW, that is part of the Citus package. Nowadays, I think what you would probably want to do is just download the Citus DB extension. You don't have to use the cluster features to get the column store. But the column store FDW gives you the ability to store data within Postgres on disk in a columnar format. One downside to CStore FDW is that it does not currently do any wall logging, so you cannot use this and get a point-in-time backup. You also cannot use this with binary level replication. But this is where some of those other features come in, where you can potentially, replication would be difficult, but I believe you can get a PG dump of the data that's in a CStore FDW column store. There is also an in-memory column store. So for certain types of analytics, being able to read memory off of a disk into a column store and then perform operations on that column store in memory can be beneficial enough to warrant just reading it back in from disk. There's also a MonetDB foreign data wrapper. So MonetDB is a dedicated column store. It's a completely separate database engine, separate database technology, but because of the foreign data wrapper, you can now talk to Monet from within Postgres as if it was a native Postgres table. Did anybody know that there's GPU support for Postgres? Nobody. One person. Oh, well, you. PG Strom, this was done by the folks at NTT Data, and it is GPU level computational support for Postgres. The nice thing is that once you load the extension, that's all you have to do. Just say, hey, here's the extension, load it. You do have to load, there's a configuration parameter you have to put in postgres.conf. But once you do that, operations such as sorting that can potentially make use of GPU support just automatically happens. So sorting, I don't remember whether there's features other than sorting, but certainly sorting can make use of GPU and can be significantly faster than doing CPU-based sorting. This can become very important with predictive analytics, where a lot of times you're dealing with essentially what are matrix representations of something that you're modeling, and that ability to perform sorts against it, certain other things against it, that becomes, being able to do that on a GPU becomes very valuable. Aside from PG-STROM, through the stored procedures, you can potentially also gain GPU support. So PL Python, there are Python packages that allow you to handle GPU, basically GPU optimized Python code. So if you pull those into a PL Python function, now you can run a computation right on the database where the data lives, but still gain the advantage of CPU performance. Postgres has a very strong, very robust community. Hopefully, this is something that you'll see here just attending the conference. This community means that there's lots of different features, new technologies that people are constantly developing to work with and around Postgres to make it easier to do certain things. I've got 3 different examples of that I will show here today, but keep in mind, this is a list that is constantly evolving. There's people constantly creating new things for Postgres and using it really as a data platform. So PostgREST is a RESTful API for Postgres. It allows you very easily through Postgres stored functions to present a web interface to the rest of the world. ToroDB, is anyone here also using Mongo? ToroDB speaks the MongoWire protocol, but stores the data in Postgres. It can actually use other relational databases, but it's geared primarily for Postgres. The nice thing about this, first of all, it's faster than Mongo. But on top of that, you gain this relational representation of the JSON that you've handed off to ToroDB. So you now have the option of you can use this data in its native JSON format through the Mongo protocol or from within the database. You can get the JSON objects back out and deal with it as JSON. But the other option that you have is when you know a little bit about the structure of particular JSON documents, this data, Toro does not store the data as a JSON field in the database. It actually decomposes the JSON document into multiple tables. So if you have a document that has an array of objects, that array of objects becomes rows in a table. You can do aggregation against the rows, you can do filtering against the rows, you get all the relational capabilities that you expect from a relational database, and it works transparently with unstructured or really semi-structured data in the form of JSON. Finally, Madlib is straight from their website, big data machine learning in SQL. What that means is that they are taking well-known, understood machine learning algorithms and modeling techniques that you would see in R or Python or other packages, and they are implementing them in this open source project in a combination of Python and SQL, so that now your modeling can be run directly on the database. Again, this is going back to the notion of run data-intensive stuff where the data lives, reduce the size of the data that you're dealing with as quickly as possible, and then if you need to do more sophisticated, maybe more compute-intensive stuff where you need a larger cluster of machines, things of that nature, well, now there's a smaller set of data that you can go ship somewhere else to run the heavy lifting on. But many of these algorithms are not terribly CPU intensive, so you can actually do a significant amount of work running straight on the database, and MADlib is geared towards making that easier. So I wanted to kind of pull all these ideas together in a single example, and what I'm using here is there's I wouldn't call it a university, but it's a company called Galvanize that teaches, all that they do is teach web development and data science. So this is from a final project that one of their students just did down in Austin, where she built a system where you can upload an image of a face, and it will attempt to characterize the emotions of that face and give you an emoticon or an emoji that matches that. So the way that the system operates is I'm not sure what just happened. The way that the system operates is the image goes through convolution layers, and really these convolution layers are there essentially to mimic what human vision does. So they take the complicated image and they break it down into a series of much smaller, much simpler images. Those images are then fed to a fully connected neural network, which makes the actual prediction. So one way that this could be she ended up implementing this in a more traditional approach using just Python, and I believe that she's using Mongo for storage. But you could implement this same system using Citus so that you've got scale. You can shard across as many machines as you need to. You can take the images, you can store them in the BiDirectional data type so that you don't have to worry about managing file systems and things of that nature. Or you could use an object store in a foreign data wrapper, or if you wanted to manage something like something as potentially as simple as just a network mounted file system and just use a regular file system level access to be able to get at the raw image data. The PandaPost ND-array data type that I mentioned earlier, those the output of the convolution layers is it's a pandas ND-array. It's just essentially a one-dimensional matrix. So that can be represented using PandaPost. You can use MADlib to do the machine learning algorithms and the really cool stuff. And then in terms of API, you could use Postgres, continuing the tradition of poorly naming technology that Postgres itself started in 1995. You could use Postgres to present the API that then your web front end would connect to have the predictions made. All happening entirely within Postgres. So I do want to point out that there is no such thing as a magic bullet. There are absolutely machine learning and big data problems that Postgres is just not a good fit for, at least in terms of storage. But what I think people need to do is shift their thinking of how they think about Postgres. Instead of thinking of Postgres as, oh, it's a relational database, Postgres is really more of a data platform. It allows you to operate with data in ways that are frequently much easier than other alternatives. It allows you to connect to different data sources. It allows you to pull data together as necessary, when necessary, just in time. It provides a tremendous amount of flexibility with what you can do with the data through stored procedures, through the different extensions. And it does have a world-class relational database engine. So you do have that available to you as well. So if there are parts of your system that do rely on transactional semantics and where data quality is a prime concern, you can make use of that at the same time that you're doing data science and potentially using other technologies. Questions? I put everybody to sleep. I win.
So, do you find yourself working on like a data science sort of scripting problems, like you use PL/R, PL/Python in your day-to-day work?
I am not a data scientist. I just play one on TV or on stage. So no. However, I have built systems for clients to make it easier for their data scientists to do these kind of things. In particular, we do have a client where their data science is being done directly inside of Postgres because it's a financial institution, and there's certain concerns that exist in regulated industries about being able to demonstrate things to regulators, such as, why did you make this lending decision? Was it based on race or was it not? And having the ability to do the data science within the database means that you can tie that stuff together better. The other major advantage that it can give you is a very common paradigm for predictive analytics is that you will have your analysts, or call them now data scientists, they're over here, and they're on this side of the office. And then you've got your coders over here who are writing your Rails app, and trying to get these two to play nice together, no, not so easy. So by providing the ability to run the analytics directly inside the database, not only do you potentially gain the benefit of run the calculation where the data lives, but you can actually set up an environment where you use the exact same code to do your training, maybe not the exact same code, but you use the same general code to do your model training as you then use to run the model itself. So the problem with this split brain approach is they'll use one completely separate set of techniques using maybe R or Python or what have you. They're writing SQL to pull the data out. In my experience, they're often writing rather ugly SQL to pull the data out. And there's just this big disconnect. And then finally they create a model, and they represent the model essentially. Maybe it gets represented in Python, maybe it's something that's written down as a bunch of specifications. They toss it over the wall, and now your Ruby guys are going, well, we're not running Python, so we're going to recode all this. And now you don't know if it works. So now there's a whole bunch of revalidation that has to happen. With Postgres and with the procedural languages, if they want to use R, let them use R. You're not going to run the website in R. Heavens no. That would be a horrible idea. But you can run the R right inside the database. They don't need to be concerned about it. And now you can develop your model code in such a way that, look, the model code is just what, you basically just push it straight out to production. Do some performance testing, maybe make sure it's not going to blow anything up, but there's not this entire recoding, revalidation issue that comes into play. Those guys are currently pre-production. My expectation would be that they'll probably be in the terabyte size range once things get rolling. So certainly not enormous. I know.
Not big data, but big data.
Right. We'll call it medium data. So I know a friend of mine. I don't know how much of this I can actually relay, but a friend of mine is doing the big data architecture for an auto manufacturer, and they want to be able to do analytics on data that's coming back from the cars, and they're talking many petabytes. So that's actually, I suspect you actually could make that work in Postgres if you wanted to put the effort into the sharding side of things. I don't think it's completely out of the realm of possibility. Would that make sense? I don't know. And certainly a big part of the question is, okay, how heavy is the computation that you're doing? Because if you're doing something that's extremely computationally intensive and not so much data intensive, the ability to run the analytics inside Postgres can become a hindrance as opposed to a help. But the size of data that you can successfully manage in Postgres, I mean, 10, 20, 30 terabyte databases are not that big of a deal. They're not that uncommon. So as the technology improves, and by the way, that's straight in Postgres. That's not even using something like Citus. So now if you're using Citus and if you paired it with moderately beefy hardware, who knows how big it could get.
Is there any sharding things supported by Postgres?
Question was, is there any sharding supported with Postgres? Postgres itself does not provide any direct sharding support. There's been some discussion of this, and there may be something that happens in that realm. Declarative partitioning is something that's probably going to land in 10.0. So it would be interesting to see, okay, with the declarative partitioning, is there a tie-in between that and sharding? Because they're similar problems, clearly. But the nice thing about Postgres is because of the enormous extensibility that it offers, you don't have to put it in Postgres. Citus was able to build a company based on straight community Postgres, no modification of Postgres at all, just creating this extension that uses things like, oh, let's plug into the planner and let's plug into the executor so that when we see a query come down, oh, hey, this query, it's hitting a bunch of sharded data that's on all the worker nodes. There's a master node that you have in the Citus architecture. You run the query against the master node, and it intercepts it and says, whoa, hold on, timeout. This table and this table and this table, they're sharded out, so we're going to figure out, okay, we need to spread this query here and this query here and this query here. Those nodes do as much work as possible, then they take the results and they hand it back to the master node for whatever needs to be done in the final solution. So it's a quite sophisticated architecture. It's very similar to the architecture that Greenplum built, but Citus had the advantage of starting several years after Greenplum. So when Greenplum built, I think the product name is just Greenplum MPP. When they built that, they had no choice. They had to actually make modification to Postgres code itself, and that's why it's a fork. Citus had the huge advantage of when they came around, people had done enough work to get more extensibility and that they were able to just plug right in. So because of that, there's other things that are a bigger priority for the community. At some point, the community may well support sharding directly, but I don't know of anybody that's directly working on that at this point. Other questions? Great. Well, if you think of any other questions, I'll be here for the rest of the conference, or drop me an email. Thanks.